Okay, we're going to review some topics in centripetal motion with a little touch on energy. Centripetal motion basically is circular motion, and the reason why it's called centripetal is you can see in the picture to the left there that the acceleration of anything moving in a circle always points toward the center of that circle, hence the term centripetal acceleration. And the velocity of the object is tangential to the circle. So first of all, we need to define what acceleration and what it can mean. Okay, so first of all, we must remember that velocity is defined as a speed in a particular direction. Acceleration is a change in velocity. Therefore, this means that acceleration could be changing the speed, or changing direction, or both, changing speed and direction. So let's go over how the direction of forces affect the airplane's motion in terms of speed and direction. Let's start with speed. So if you have a net force that's parallel and in the direction of the airplane, that force is going to speed up the airplane according to Newton's second law. And similarly, if the net force is going against the motion of the airplane, it's going to slow it down. But what happens when the force is perpendicular to a moving object? Well, whenever that happens, what's going to happen is there's going to be a curved left turn for that airplane, meaning that airplane's going to have some circular motion because it has a centripetal net force. And similarly, if that force is on the other side of the airplane, it's going to be a banked right turn for the airplane. And notice the force points toward the center. So let's review and summarize what we just learned. So in summary, forces that are tangential or parallel to the motion, those forces are the ones that change the airplane's speed. Forces that are perpendicular change the airplane's direction. And whenever you have circular motion, your two axes should be these two axes, the one that's pointing toward the center and one that is tangential. We have equations for centripetal motion. The centripetal acceleration is directly proportional to the square of the velocity and inversely proportional to the radius. And of course, you can always use Newton's second law even on the perpendicular, except in this case, the acceleration it's talking about is centripetal. So let's go over free body diagrams, and we're going to use the roller coaster loop as our example. So look at the card at the bottom of the loop. What forces are acting on it? Well, the force of its weight is trying to pull it down. But what keeps it up is the track. Now, notice how I drew the normal force of the track to be longer than the weight force. And the reason why is because we know that that cart is about to go into circular motion, and therefore you need to have a net force pointing toward the center. Okay, now let's say the car gets to here. What forces are acting on it? Well, we have the weight of the cart trying to pull it down. And this time the normal force, which is always perpendicular to the object it's touching, is pointing toward the center. So now you can see here on the side of the loop, they're both playing a different role. So the weight is down, and since that force is tangential to the circle, weight at this point is slowing down the roller coaster. The normal force is pointing to the left and pointing toward the center, and therefore it's the normal force which is responsible for the change of direction. Okay, now the things at the top. Now at the top, we have the weight pulling down on it, and the normal force is also pushing down on the cart. So there's two forces trying to bring the cart down. Now notice that they are both going toward the center, and therefore both forces are responsible for changing the direction. All right, let's talk about free body diagrams at a more generic spot on a loop. You could also do this if you had a pendulum. So we have the weight pulling down straight down, and we have the track pushing normally against the cart toward the center. Now on a test, that's exactly how you would draw a free body diagram to get all the points. Because on the test, when they ask you to do a free body diagram, you never do components. If you want to draw the components, that's called a pseudo-free body diagram. And you must define your axes first. Well, since this is circular motion, the first axis that we're going to define is the centripetal axis, meaning the axis that goes through the center of the circle, and the tangential axis. The normal force is pointing at the center, is already on the centripetal axis, but it's the weight force that's not on either, and therefore we have to find its components. Well, to do that, we have to know the angle. Well, using a basic geometric principle, that both angles are called transverse angles, and you can look up the geometry of transverse angles. So using that theta, I can figure out that going into the track is mg cosine theta, and going along the track is mg sine theta. It's kind of interesting how it's still kind of like sine slides. So as you can see here, the weight is playing two roles. On the one hand, the weight is trying to prevent a change in direction, and on the other hand, it's also trying to... Okay, so we're going to solve example 1, which is called calculating the critical speed. The critical speed is the minimum velocity it takes to get around a loop. And in this question, we're going to both calculate the bottom and top speed, such that the cart does not lose contact with the track. Okay? As roller coaster designers, we don't want our cars falling off the roller coaster. So whenever you get a question like this, the key word is losing contact. That's basically code for no normal force, because normal forces only exist if there is contact occurring between objects. So basically, I'm going to refer back to the free body diagram that I drew earlier and use Newton's second law. Now, Newton's second law in this particular case is the centripetal version of it. So I'm doing perpendicular centripetal forces and centripetal acceleration. So normally, the normal force and the weight are both contributing to the centripetal motion. And since it's centripetal motion, I can plug in the formula for centripetal acceleration. Now, if the track loses contact with the cart, that means the normal force is going to equal 0. And this is my equation. The masses cancel out on both sides. Now notice how interesting that is. That means that the critical velocity does not matter on how heavy the cart is. It only matters on the radius of the loop and on the gravity of the planet. So we're going to solve for velocity. I'm going to multiply r on both sides, take a square root, and there we go. The speed at the top of the loop, tangentially, has to be the square root of g times r. Now let's answer the other question. How fast does the cart need to be at the bottom of the loop so that it can reach the top of the loop with that speed? To do this question, I'm going to approach it with energy. In energy, we like to define a zero line. And for roller coasters, we tend to do this at the lowest point of the roller coaster. Therefore, at the bottom, we have no potential energy because the cart is at the zero line. It only has kinetic energy. And then as it goes up the loop, it's going to slow down and have less kinetic energy. But then it's going to gain some potential energy because it's at a higher point. Using the law of conservation of energy, which means I'm assuming there's no friction, the energy at the bottom has to equal the energy at the top. The energy at the bottom is just kinetic, And at the top is both kinetic and potential energy. I plug in the formulas for kinetic and potential. And I notice here that since every single product has an m in it, they cancel out. So once again, the mass doesn't matter. I'm going to multiply 2 on both sides. And I'm solving for VB. Well, there's a couple things I need to change here. First of all, I'm trying to figure out how fast I need to be at the bottom in order to get to the top at the correct speed. So I'm going to plug in that number at the top. Also, the height of the loop is basically a double radius. So plugging in those numbers, that's what I'm going to get. And you're going to see here I have 4 GRs plus a GR, which is 5 GR. I take the square root, and boom. That is the tangential speed required at the bottom of the loop. All right, we're going to go over another classical energy problem in terms of being a pendulum, but it's also circular motion because the swing is in a circle. So pause the video right now and read those 3 questions. Welcome back. Okay, so let's answer question A, which is how much lower is Tarzan from where he started his jump? Now to do this, we don't need physics. We only need geometry. If I draw a line here, you can see that we have a right triangle at the top there. And this side of the triangle is the cosine of that angle. Now, the length of the rope doesn't change. The rope will always remain 6.4 meters. Therefore, to find the height, I just need to find the difference between the rope and that side of the triangle. So basically the height is going to be 6.4 meters, the length of the rope, minus the length of the rope times cosine 40. Plugging that in, we're going to get a height of 1.5 meters. The next question is if he jumps from rest, what is his speed at the bottom of the swing? Okay, so we're going to use energy. We're going to define the zero line at the bottom, meaning that's the lowest point, and therefore I like to call that point 0. At the top of the swing, he has all the energy he's going to get, and it's completely potential. Notice he's starting from rest. There is no kinetic. He releases his feet, he's going to swing down, and at the bottom, he's going to have only kinetic because he has no more height, but he has a lot of speed. So this is a simple conservation of energy question because basically the potential energy at the top equals the kinetic energy at the bottom. Plugging in the formulas for potential and kinetic, we notice that the masses cancel out again, meaning that mass doesn't matter. Aristotle is wrong. And there we get GH equals half V squared. Multiply 2 on both sides and then take a square root. And that's how you calculate the velocity at the bottom of a swing. Plugging in the numbers, we're going to get 5.48 meters per second. Okay, let's go over question C, which is more relevant to our topic of centripetal motion. The question is how much tension is going to be in the rope at the bottom of the swing? Well, since the question is asking for a force, it is upon us to draw a free body diagram at the bottom. At the bottom of the swing, we have the earth pulling down on the object and the rope pulling up on the man. Now, why did I draw the tensional force larger than the weight force? The reason being is because it's centripetal motion. And if I have circular motion, that means the net force has to be pointing toward the center. The tensional force has to win the battle. So let's use Newton's second law for centripetal motion. Here I'm going to define pointing toward the center as positive, and therefore the weight is counteracting the tension in the negative direction. I add that to the other side of the equation, and here I have the expression that says the tension of the rope equals mass times the acceleration plus mass times gravity. meaning the tension of the rope not only has to carry the man's normal weight, but an additional amount for centripetal motion. Plugging in the formula for centripetal motion, I can now get my answer by plugging in the numbers. And plugging in the numbers, I see here that he's going to be 234 newtons because of circular motion, and the additional 500 newtons due to his weight, for a total of 734 newtons.